Dear students, in the last lecture we studied about set theory, different types of sets and some definitions, etc. In the next chapter, in this chapter we will continue the same thing but some extra things, and we'll start with the null set and or empty set. So what is null set? The set that contains no element is called the null set or empty set and is denoted by phi. For example, P is equal to x such that x square is equal to 4. X is odd. That means what? X is such that x square is equal to 4. When x square is equal to 4, the value of x is plus minus 2, and it is saying that x is odd. That means this one is empty. There is no element in this which is odd because x has value plus or minus 2. So this set has two elements plus and minus 2, but the x is defined as x is odd. That means he wants the odd one. So there is no element here. There is no such elements which is odd over here. So this one is empty set. Similarly, you can see the example q is equal to x such that x square is equal to 9. X is even. Now x is equal to plus minus 3, and he is saying that x is such that this is equal to this and x is even, which is not possible here. That means there is no element, even element here. There is no element even. That means this is empty set. There is no such set element here. Similarly, one example, r equals to x such that x square is equal to 9 and 2x is equal to 4, x is 2. That means there is no element, such element. So in this way it is defined as what is null set. The set phi equals to 0. This is not a null set because 0 is the element of the set. This is an element of the set phi. The set A is equal to phi is not a null set because phi is the element of the set. You got it? Now we will see power set. What is power set? The power set of any given set A is the set of all subsets of A and is denoted by PA. If A has n elements, then PA has 2 to the power n elements. See here, if A has n elements, then power of set A has 2 to the power n elements. See the example. Set A has two elements R and S. Then its subsets are, how many subsets will be there? Phi is one subset, R is one subset, S is one subset, and RS. That means power of set has total 4 elements. How it is? Phi, R, S, RS. These are all subsets of A. And the elements now, power set of A has the elements, 4 elements. Now universal set. What is universal set? If all the sets under investigation are subsets of a fixed set U, then the set U is called universal set. For example, in plane geometry, the universal set consists of all the points in the plane. Now we will see comparable and incomparable sets. Two sets A and B are comparable if one of them is subset of other. that is A subset B or B subset A. If A subset B and B subset A, then A equals to B. Set phi is comparable to every set. Every set is comparable to the universal set U. See the definition. Every set is comparable to the universal set U. Two sets A and B are said to be incomparable if A is not the subset of B and also B is not the subset of A. That is, there is at least one element in A which is not in B and vice versa. Now we will see some theorems based on the above set theory. Theorem 2. Theorem first we have discussed in the last lecture. Prove that every set is a subset of itself, that is A subset A. So what you will do, let X belongs to A. X belongs to A. That implies X belongs to A. Again you can write, therefore A is subset of A. As every element belonging to set A is also an element of set A, therefore A is subset of A itself or itself. Now see the theorem third. Prove that if A is subset of B and B is subset of C, then A is subset of C. See, from the theorem itself, A is subset of B. That means in A, suppose the A set has some elements and they are also in B, and B is subset of C, so indirectly A is subset of C. Now see how will you prove it. Let X be any element of the set A. Fine. Therefore A is subset of B. Now since A is subset of B, therefore X belongs to A. That implies X belongs to B also, because A is subset of B, and I have assumed that let X be any element of set A. Since A is subset of B, therefore X belongs to A. So definitely that implies X belongs to B. And B is subset of C, therefore X belongs to B. Since X belongs to A implies X belongs to B, and X belongs to B implies X belongs to C. Therefore what? X belongs to A implies X belongs to C. Therefore A is subset of C. Got it? Theorem number 4. Prove that if A is subset of B, B is subset of C, C is subset of A, then A is equal to C. Proof. If A is subset of B and B is subset of C, then A is subset of C. C is subset of A given. You just see from this one. I am writing this one from the above theorem itself, because if A is subset of B and B is subset of C, that implies A is subset of C, and in the theorem itself there is one point given, C is subset of A. It is given. This means what? Since A is subset of C and C is subset of A, that means A is equal to C. See, A is subset of C and C is subset of A. That means what? A is equal to C. Theorem number 5th. Prove that if A is subset of phi, then A is equal to phi. Phi is subset of A, as phi is subset of every set. But A is subset of phi, therefore A is equal to B, phi. Now what is equal sets? Two sets A and B are said to be equal and written as A equal to B if both have the same elements. Therefore, A equals to B implies that X belongs to A, and this also says implies X belongs to B. If some elements in set A that does not belong to set B or vice versa, then A is not equal to B. That means to get the equal sets, what is needed? If X belongs to A, that implies on both the cases that X also belongs to B. See one example to discuss. See one example to discuss. A equals to X such that X belongs to 10. Sorry, X such that X is less than 10 and X is even. This means what? We have to take the terms up less than 10 and those terms which are less than 10 and even, and they are even. So if we start counting 1 2 3 4 5 6 7 8 9, you cannot take 10, but also you have to take the even terms. So we'll start 2 4 6 8, that's it. And C equals to X such that X is greater than 1 and X is less than 10 and X is even. All these three things imply the same thing, that all three sets are equal. Now we'll discuss operations on sets. Operations on sets. What are the operations? Like union of sets, intersection of sets, difference of sets, etc. We will discuss one by one. First we'll discuss union of sets. What does it mean? Union of two sets A and B is defined to be the set of all those elements which belong to A or B or both and is denoted by A union B. Union of two sets A and B is defined to be the set of all those elements which belong to A or B or both, and it is denoted by A union B. See, this was A union B equals to X such that X belongs to A or X belongs to B. You have to take all those elements which are either belongs to A or B or both. For example, let A is equal to 1 2 3, these are the elements, and set B has element 3 4 5 6. So you have to, A union B will be 1 2 3 4 5 6. These are either belonging to A or B or both. You have to take one, each one at a time. That is 1 2 3 I have taken. I am not repeating again. I have taken once 3, then 1 2 3, now 4 5 6. Now next one is intersection of sets. Intersection of two sets A and B is the set of all those elements which belong to both A and B and is denoted by A intersection B. See this one. Intersection of sets A and B, two sets A and B, is the set of all those elements which belong to both A and B and it's denoted by A intersection B. How will you write the definition? A intersection B equals to X such that X belongs to A and X belongs to B also. Take one example. Let A is equal to ABCD and B is equal to ABLM. In these two sets, which elements are common? You can see AB is here in the set A and AB is also in set B. The rest of the elements are not common. So then A intersection B is AB, because these two elements are present in both the sets. See, therefore A intersection B will be AB. Now difference of sets. Difference of sets. The difference of two sets A and B is set of all those elements which belong to A but do not belong to B and is denoted by A minus B. That is, A minus B equals to X such that X belongs to A and X does not belongs to B. Suppose X in the A set, okay, you can see here example is given. A is equal to ABCD, B is equal to DLMN. So according to the definition, you just see the difference of the two sets A and B is a set of all those elements which belong to A but do not belong to B. You see the element which are in A but not in B. You see A, B, C, D. D is here, L, M, N. So A, B, C, three elements are in A are not in B. So A minus B will be A, B, C. Now we will solve some questions. Prove A union A is equal to A intersection A is equal to A. See how to solve it. We know B is a subset of A union B. You assume just B is subset of A union B. Therefore, A is subset of A union A. Let X belongs to A union A, and that implies X belongs to A or X belongs to A, and that implies X belongs to A. Therefore, A union A is a subset of A, as A union A subset of A and A subset of A union A, that implies A is equal to A union A. So in this way I am completing the second lecture, and we will discuss some more in the next lecture. Some problems will be discussed, and I will try my level best to sort out your problem. So thank you so much.